All right, so let's look at this proof of this claim here, that 1 plus square root of negative 3 is irreducible but not prime in this ring here. I wrote the proof of the irreducibility over here, and the start of the proof that it was not prime down here. So go through this argument, think with me here. Claim that this is irreducible in that ring. What does that mean? It means if you can factor it as x times y, then one of those must be a unit. So x over y must be a unit. The norm is the key thing to help you as a problem-solving tool to finish the proof, and that's the case in many of the proofs like this here. The norm of 1 plus square root of negative 3, if you got this factorization, is going to be the same as the norm of x times y, which by property 2 of norms is norm of x times norm of y. But hey, the norm of this thing is, if you plug it into the formula, it's 4. This is the absolute value of a, 1 squared, minus d, d is negative 3, times b squared. B is 1 as well. The coefficient of the square root of negative 3 is 1. This simplifies to 4. You can get rid of the absolute value signs. Simplifies to 4. But if x and y are not units, then their norms are not 1. But the norm does have to be an integer, so they must both be 2. But that's impossible, because it would mean there are integers a and b where this is true, because this is the general form for the formula for the norm for this example. In this example, you can write that for the norm. The two negative signs cancel to give you this, and this is never negative, so you can get rid of the absolute value signs. It would mean this is true for some integers a and b. That's impossible, right? There's no way that can happen. No way they can give you 2. 2 is not a perfect square. And it's not a perfect square for sure of an integer. It's not a perfect square of a whole number, of a rational number either. There's no a and b that can give you that. So that means, that's a contradiction. It means either x or y must be a unit. So therefore this thing must be irreducible. Why is it not prime? Well, the first thing is a little trick, just to note that if you multiply this thing times its conjugate, its complex conjugate, you get 4. Check that. You can see that it simplifies to 4, which is 2 times 2. So this number here, 1 plus square root of negative 3, divides, this is a divide symbol, divides 2 times 2. If it were prime, then it would have to divide each of those factors. It would have to divide 2. Claim it does not divide 2. This does not divide. That claim needs to be proved. Anything argued by contradiction. Essentially, you can try to argue why there is, if you assume there was such a factorization like this, if you assume to the contrary that 1 plus square root of negative 3 divides 2, you can get a contradiction out of this. If you expand this out, this ends up equaling a, let's see, square root of negative 3 times square root of negative 3 is negative 3, times b is negative 3b. That's the real part. And the imaginary part, I won't put an I in there, we'll just put a square root of negative 3. Is going to be b plus a in front of that, from the outside and inside terms. If this is going to be true, then a minus 3b would equal 2, and a plus b would equal 0. But this has no integer solutions. That technically should be verified. You can subtract one equation from the other to cancel the a's. You get negative 4b equals 2. So b would have to be negative 1/2, not an integer. And a would not be an integer solution either. This has no solutions of a and b that are integers. Okay? And that would be a contradiction. So this claim is true. So this thing is irreducible, but not prime. They are distinct concepts. In general, in integral domains. All right, now we're going to go through some theorems pretty quickly here. I've got some of the proofs. I think for sake of time, I'm not going to be able to go over the proofs, but they are there, and they're not super hard. But they can be certainly things you get stuck on if you were trying to do them from scratch. So it's worth studying and thinking about. In an integral domain, every prime is an irreducible. We just saw that not every irreducible is prime. But it does go the other way. Every prime is irreducible. Here's the proof. You can see it's not too hard. It's, if you were, again, going to do this from scratch, it's a little tricky. But put this on the test. Again, maybe a hint or two should help you finish it. Next theorem. In a principal ideal domain, PID, an element is irreducible if and only if it's prime. In PIDs, they're equivalent concepts. Evidently, then, this ring up here is not a principal ideal domain, because otherwise it would contradict this theorem. Got the proof of that here as well. Actually, just the idea of the proof. This proof is a bit trickier, for sure. Got the main idea here. The trickiest part is actually at the end that I kind of skipped here. But I think it's still definitely worth studying and thinking about to understand things better, even if it's maybe too tricky for an exam. Or if I did put it on the exam, I did do like that one problem where I just had you fill in the blanks, essentially, in the proof. Don't take the time to look this over. We need to get going on to the next slide here. Although you could, it's in the book as well. Two more big concepts in this chapter. One is that of a unique factorization domain, and another is something called a Euclidean domain, which actually I already talked about a little bit the other day. Maybe it's worth not writing these down, just other than just writing what we talked about. It might be worth just sitting and thinking here. The content is on pages 312 through 317, essentially. An integral domain D is called a unique factorization domain, UFD, if essentially the fundamental theorem of arithmetic holds. We have unique factorization in terms of irreducibles. We say irreducibles, not primes. Two properties. Every non-zero element of D that is not a unit can be written as a product of irreducibles, which in Z are the same as primes. And the factorization into irreducibles is unique, just as it is for Z, up to associates and the order in which factors appear. Now with the fundamental theorem of arithmetic with integers, we just say it's unique up to the order in which the factors appear. We don't really typically say up to associates, though that technically is in the background if we allowed negative integers in our factorizations when we're talking about primes. When we first talk about primes, we don't typically talk about negative factors, but we could. So then up to associates would mean, you know, if you got two factors of 7, you can also think of it as two factors of negative 7. 7 and negative 7 are associates. In the more general context, it's definitely good to emphasize that. Up to associates. Theorem. Every PID is a UFD. Every principal ideal domain is a unique factorization domain. The analog of the fundamental theorem of arithmetic holds in principal ideal domains. Proof of that's pretty hard, actually. Maybe not, maybe hard is the wrong word, it's long, unpleasant. Okay? It's based on something else that I have not talked about in this chapter, which is actually a big thing. It's called the ascending chain condition. And I don't think I want to talk about that today, but it's based on that. Corollary of it, if you got a field, then the polynomial ring with coefficients on that field is a UFD, because we already knew it was a PID. Remember I said that? That was in the book. Rings of polynomials where the coefficients come from a field are principal ideal domains. Rx, for example, is a principal ideal domain. Polynomials with coefficients from real numbers. And therefore, by this theorem, it's also a unique factorization domain. Here's something worth knowing, though, that's kind of a contrast. Zx is actually not a PID. Z is. The integers are definitely principal ideal domain. But the ring of polynomials with coefficients in Z is actually not a PID. I don't know if we've mentioned an example of something that was not a PID before. For example, this ideal, generated by x and 2, is actually not a principal ideal. The book does prove that. It's worth looking at. If you thought of this as an ideal in Rx, coefficients in R, actually it is a principal ideal. And in fact, it would equal the entire ring Rx. And you could also say it's generated just by 2, for example, because 2 is a unit in Rx. And remember, whenever your ideal contains 1 or contains a unit, it equals the whole ring. Remember that? So it is a principal ideal in Rx, but not a principal ideal in Zx. However, based on the theorem in chapter 17, it's still a unique factorization domain. You may remember from chapter 17, among all the other things in chapter 17, there was a discussion about unique factorization in Zx. Page 297, 298. And they had this application of unique factorization to weird dice. Okay. So in spite of the fact that it's not a PID, it is a UFD. There are unique factorization domains that are not principal ideal domains. Another example to think about is similar to the example we just thought about. This ring, I made it the square root of -5. I could have made it the square root of -3 as well, is actually an example of a ring that is not a UFD. And one of the completion problems for next Monday to work on, and I would strongly suggest working on this one, and this was my favorite problem, by the way, in making the key. Show that 21 does not factor uniquely as a product of irreducibles. It's got a couple different factorizations where those factors are not the same as the other factors in the other factorization product, 2 associates. 21 is certainly 3 times 7. You need to verify 3 and 7 are both irreducible in here. It also turns out to be the product of 2 complex numbers that are what are called complex conjugates of each other. And it's not too hard to find the other factorization, actually, especially if you know about complex arithmetic. I'll give you a hint. If you want to do it from scratch without looking at the key, try to write it as a plus b square root of -5 times a minus b square root of -5. Write it as the product of 2 complex conjugates, they're called. Talk a little history now. And this is actually another really interesting part. Historically speaking, this stuff has been very important in pure math. Fermat's last theorem. Back when I was your age, 1980s, just dated myself, Fermat's last theorem had not been proved. Here's the most famous unsolved problem in math. Well, about 1993, my first external email came into my inbox. Okay, what does that mean? Back in the late 80s, early 90s, we actually did have email, but it was all internal. It was like, I was a student here at Bethel. I got emails from my friends at Bethel, The thought never occurred to us to send emails to people outside of Bethel. It was all intranet, internal internet. There was no external. I mean, I guess the infrastructure was there to an extent. But it never occurred to people that they'd send an email to somebody outside of your organization. Maybe it occurred to some people, just not me. My first external email, 1993, June. Fermat's last theorem solved. I'm like, what is this? Who's this from? What? I don't know this person. It's in grad school. Somebody not from the U of M. They claimed Fermat's last theorem had been solved. And so I'm like, wow, that's pretty neat. Didn't know the backstory of it until I started teaching here 5 years later. And I was teaching Foundations of Math and found out there was a NOVA 1-hour program about the person who proved Fermat's last theorem named Andrew Wiles. I'll give you the link on this sheet here, on this PowerPoint slide. The link is there for that. We'll come to that in a minute. The book goes through the history of it. Proofs in the case, what is Fermat's last theorem? I didn't say what Fermat's last theorem is. It's that this equation right here, x to the n plus y to the n equals z to the n, has no non-zero integer solutions when n is an integer greater than or equal to 3. It's got plenty of solutions when n is 2, right? Think Pythagorean theorem. Certainly plenty of solutions when n equals 1. But when n is an integer greater than or equal to 3, this has no non-zero integer solutions. That's the gist of Fermat's last theorem. It's historically important because Fermat claimed to have a proof of it, but he never showed anybody the proof. And people tried to prove and they couldn't in the general case. Proofs for special cases were given. N equals 3, 4, 5, and 7 were done by Fermat himself. Euler in the, I think, 1700s. Dirichlet and Legendre in the early 1800s. Gabriel, I'm not sure how to pronounce this. It's French. Lame? Not sure. Thought, that's supposed to be thought. Thought he had a full proof in 1847, but he incorrectly assumed unique factorization in Z alpha, where alpha is what's called a complex primitive P through unity for an odd prime P. So he made an incorrect assumption in this proof, and that's common in faulty proofs, is making an incorrect assumption about something. Maybe, usually you're assuming it because you think it's obvious or because you just don't think about it. Those are the two reasons people make that kind of mistake. Ernst Kummer, German, I think, partially fixed Lam's work and proved it for all exponents less than 100, prime or not, except for 37, 59, 67, 74. You know, who knows the nature of his proof without looking into it, why he couldn't prove it for those cases. It was Andrew Wiles who finally proved it in 1994. I heard about it in 1993, and this is where the story gets interesting. They made it into this NOVA 1-hour program. That's my favorite math video ever on pure math. They make it really, really dramatic. You've got to watch this video. Melissa has watched it. About how he worked for 7 years on this problem, and he finally solved it. But there was actually a mistake in the 1993 version, and he was really stressed out about it, trying to fix it. Took him a year and a half or something. Finally, working with somebody else, he fixed it in 1994. It's a link to, I think, the library's. Well, this might be the PBS site for it, but our library has a VHS of it, actually, that you should watch, okay? I'll send you the library code. It's so good. It's the best pure math documentary I've ever seen. Great music, great drama. It really is. I'm being serious, being completely serious. They make the mathematical life seem so dramatic. The editing in it is just awesome. It's just spot on. I just can't say enough about it. And this is not all just pure math. Elliptic curves are now being applied, which is what he used to prove it. Elliptic curves and modular forms. In elliptic curve cryptography, and I've got a couple video links here about elliptic curve cryptography. It's useful. Jean-Luc Picard will work on it in the future. Ha ha ha. You know who Jean-Luc Picard is? Star Trek: The Next Generation. That's my age. That's when I was your age when I was watching it. He was the captain of the Enterprise. And they made that episode before they found out something proved Fermat's last theorem. And this link is to everybody that video clip from that show, and he's working on Fermat's last theorem. Riker comes in and says, "What are you working on, Jean-Luc?" It's like, "Oh, I'm working on Fermat's last theorem." We've got all this technology, but we still can't prove Fermat's last theorem, is kind of the gist of what he says. Has it also been solved by Homer Simpson? That's to a link to an article claiming Homer Simpson solved it. Of course he didn't, but there is a joke in it. Okay, he sort of almost solves it. He sort of writes down an equation like this that's like almost true, and these powers like involve numbers that have like 50 digits in them, and it's almost true, and that's the joke. Okay. All right. I want to show you something on Mathematica. Here, it's almost time to go. There is more content. There's 2 more slides here. Let me go over this content and see if I can do it in 1 minute, and then we'll look at Mathematica. It's in the book. I have talked about it a little bit already. Euclidean domains. Integral domain is a Euclidean domain if there's a function d called a measure. We talked about this on Wednesday. From the non-zero elements of d to the non-negative integers with a couple properties. And basically these properties, well, the second one especially, effectively say you can do the division algorithm in Euclidean domains. D is a generalization of the absolute value of a number and the degree of a polynomial. And this should look like the division algorithm here. There's some facts all related to this. This, I think, is the last slide. Yep, okay. Every Euclidean domain is a principal ideal domain. Here's even the idea of the proof. It's not too hard. And therefore, every Euclidean domain is also a unique factorization domain, because we had on that other slide that PIDs were UFDs. Another theorem, if D is a UFD, then so is its ring of polynomials. And it's also a fact that the Gaussian integers form a Euclidean domain, and therefore also a PID and UFD. But remember, the z squared root of -5, for example, and this one, z squared root of -3, are not UFDs, actually. And so they're not PIDs or EDs either. Okay, that's a very quick summary. I'm going to show you something in Mathematica that I did last night, or yesterday, I was on the phone with. And again, I'll put this in our shared folder here. I worked on visualizing these rings here, especially in the case where D is negative, though I actually did do the case where D is positive. It's not as enlightening, though, as far as the norm goes. So what I have here, this is code that creates a bunch of elements. For example, when D is -3, these are some elements from Z of square root of -3, written as lists, not written as complex numbers. As points, you might say. So this one would, for example, represent the number -10 minus 10 square root of, actually that should be negative. As a ring element, it's square root of -3. As a point that I'm going to draw in a plane, I do want a +3 there. The imaginary part of the complex number involves a square root of +3. This is code that I can use to create a plot of what? Well, these points. Like that. And you want to think of that as the complex plane. Real axis horizontal, imaginary axis vertical. And I can combine these things. And also make level curves of the norm function. multivariable calculus, level curves. These ellipses are level curves where the norm function is constant. And a key thing to note here is you can look, I made these integer values, and note that every red dot goes through one of these lines. 2, for example, has a norm of 4. It's on this level curve that represents a norm of 4. This number right here, which would be 1 plus square root of -3, notice the vertical coordinate of that is about 1.7. Or 1 plus square root of positive 3 times I, if you prefer, is on this level curve that's got where the norm is 10. So all these dots have to be exactly on these level curves where the output of the norm function is an integer. And for example, this one is on one where the value of the norm is 13. Zoom in if you need to there. And 13 is prime. Therefore, this point in this integral domain is irreducible. Remember that part of the property of norm? The output of the norm function 13, this point is going to be an irreducible point in this integral domain. Irreducible number. And as you might have guessed, I can make a manipulate from this too. And I can change the value of d here. It runs a little slow, but it eventually fixes itself. And allows you to consider different values of d. This is d equals -5, for example. But the same properties will hold. These points are exactly on the level curves that are the outputs of the norm function. Okay? So I think this is definitely worth thinking about in the context of working on these examples and the completion assignment. See you on Monday.